Hello there. Today we'll be doing matrix search. Given a two-dimensional integer matrix where every row and column is sorted in ascending order, find k0 through index smallest number. So there are several ways to do this. I think the most basic way is to turn it into a list, sort it, and then just grab the kth item. Another way is to use a heap. And the third way is use binary search. Binary search is a rather interesting approach. This is also our fastest approach. So we're going to go through three approaches today. We're going to start with the O of n space and O of n log n time. N times m time. Well, I think you'll know what I mean. Not n times m, but n plus m. Okay, let's just do it. So I'm going to start with building a list. So my list is equal to empty array, and m is equal to the length of matrix, lang of matrix 0. So we get the row and column. So for I in range of the n, which is the row, for j in range of the column. So we have all the items. So we're gonna my list dot append is gonna be matrix of I and j. So we have every single item. Now we have my list dot sort, and we're gonna return my list and the index. So it was accepted, and we're going to return submit the answer, and we have a 45%. Not too bad, not too shabby. And so as you can see, this is a n times m. Well, this is basically going through the whole entire matrix, or a sort of the entirety of n times m times log of n times m. So to sort it. So it's that's the space complexity. So space is n times m and log n times m, and no, that's not time, and space is is n times m. Okay, so we have that solution down. Let's move on. We don't want to deal with this anymore. Let's do the heap. All right, so it's still space is n times m. Well, not exactly, but our heap is size of k, which is basically n times m. Anyways, for r in range of rows, for c in range of columns, we're going to do a heap push of h and the minimum item, reverse it, because this is a max heap generally. So we're going to just little hack to get the min heap. If it is greater than k plus 1, so we're going to just pop the smallest item. Or biggest, yeah, the smallest item off, and we'll return I guess it's a min heap, and then we want that max heap going. So return the negative of that to reverse it. So let's run. We have an error. Rows is not defined. Let's see. Right. We did not define these. So n m equals lang of matrix and lang of matrix 0. Just set this as n. Oh, so this is n. So this is m, and we got it. So run. All right, a little bit slow, but let's talk about the time and space complexity. So time is going to be the time it takes to create a heap, which is n log n time. So basically the same. What's the benefit of this? Well, I think if you want to pull more out, it would be a lot easier. So it uses less space, right? Space is only k. So it saves a little space. I think that's about it for this problem. Let's get on to the binary search. This is going to take a lot of space. So I'm going to just bring this down and push this down a little bit more and shrink my face. Alright, so there might be more to it, this problem. So how we're going to do this is that we're going to look at the minimum and maximum number and count the numbers, the numbers that are below that number, and we're going to move the left and right pointer. So here's what I'm going to show you what I mean. So let me pull up my screen here, and all right. So let's say we have this matrix of 1, 3, 30, and 2, 3, 31, and 5, 5, 32 as an example, and we're looking for k equals 4, right? So we take the low of 1 and the high of 32, and we try to lose half of our take away half of our list to see if we can if it's possible for us to, if it's greater than or less than the count. So if it is greater than the count, that means we need to move the high down so that we can have fewer counts, fewer items. And if it's too low, too few counts, then we move the low up so that we can get fewer counts. So we can isolate our k, the number of counts. So let's say this is currently 16, the mid, 33 divided by 2, that's a 16, right? So 16, if we match it against the first row, we have 2 right here. Sorry, let me just give it 2 right here. We have 2 right here, and we have 2 right here. Because for each row, we're going to match it against each column, and we're going to count. We have a total of 6 items here, which is greater than k. So we need to reduce the high down to mid and eliminate that. So we have 16 now. Of course, we're going to have to reduce our mid again to get to 16 divided by 2, which is 8. And we're going to redo this. 8. We're going to remove this, and we're going to look at 8. So 8, what we have 6 again. So we have all of these. So what's going to happen is we're going to lose 16 again, and we're going to turn it into, as you guessed, 8. Whoops, 8. So now the mid is now going to be 9 divided by 2, floored, which is 4. And we're going to look at what's greater than 4, and that would be these 4 right here. So that would be 4. Is it like, is the number greater than 4? Like, is mid greater than k? And it's not. So that means we need to move our low to mid. Mid plus 1 to be exact. So here we go. Let's cross that out. Let's grab it and send it to 4 plus 1, which is 5. And now our mid is 12, because 13 divided by 2 is, floored is 12. And with that, we get 6 again. And that is, right, 6 items. So we need to move the high down. So this is currently 8, right? So we need to move it down to 6. Of course, let me erase all of this. Floor that's going to be 5, the mid. And 5 is our mid. We're going to check 5 against all of these. And let's see. We're going to get a like a 4 again, because we don't count these 5s. So k is equal to 4, so that means we need to bring the low up high again. And that should be a 5. Let's see. 6. That would be 6, because 5 plus 1. So now these are now equal. Wait, actually, what's going on? Right. We bring the high down to mid. Sorry. So these are both 5s, and we break the loop because we are done, and we return the low, which is this one right here, the 5, which is our particular item found right here. So you might be wondering how that was possible, that we were able to get that low number from a rather than getting it from the index. We were able to get it from a average. Well, what if, I mean, the question here is, what if we don't have the number, like in the array? Like, what happens then, right? Well, I don't think you have to worry about that, because we will make sure to move the high and the low between these numbers until the point where we get the correct count, and we find that that spot where where low and high crosses. All right, enough explanation. Let's just code this out. Okay, so first things first, let's set the low and the high. While low is less than high, mid is equal to low plus high minus low divided by floored divided by 2, and we're going to check if possible. So if it's possible, right, then we want to set high to equal to the mid. Otherwise, we want to set the low to equal to mid plus 1. The reason why we want to set the high to become mid is because there are currently like too many counts, too many items. It's within that item range, and we want to reduce that count to exactly the count we have, which is 4. So we reduce the number of available items by setting the high to mid. And we keep reducing. And if it is not possible, then we want to increase the low up to be higher, because as you can see, by increasing the low, we are able to get a higher number, and that way we can look at bigger numbers and expand our count. Okay, so then we return the low. So how do we get the is possible? Well, like what sort of definition is that? So this possible is going to look at our current item, and we're going to look at each column, and the count is equal to 0 for row in matrix. We're going to look at each column and check if the item is greater than our midpoint item. So if it is less than, we will subtract that column. As you can see here, we will lose that column. Let's say 30. Like we'll lose that, and we'll count from here to 2 items here. So now we're gonna add that count plus equals count plus 1, and we're gonna return the count is greater than k. If it is, like, to see if there are more counts than k. If there are more counts than k, reduce it. If there are less counts than k, increase it. And let's run it. Oh, we have an error. Let's see, invalid syntax, while greater than 0. Run it. Perfect. And submit. Very good. This is our fastest solution yet. The reason why it's so fast, because it's we're doing a log n operation, times, of course, the number of rows n log n, but we're not creating anything. We're just going through the matrix, so it's very fast. So space and time complexity. Space time is log of n. So log of n, and we have to go through each particular row and each time. So n rows. Shouldn't it be n times m? Because we have to go through each row every single time. So space is 0. Log n is for the binary search. So there is something pretty cool that we can do. It's called bisect. So we don't actually have to do a lot of this count business. We can instead look at this. We can do index equals bisect of row. This is where we can insert the x into the row, and we're going to do a count plus index, and this will also work. Oh, what happened here? Let's see. We don't need this. For row in k. Why is that there? Weird. Let's see. Sorry. Just give me a moment. Let's see. What happened here? Let's print the index. Something's weird going on here. Oh, plus equals. So this is pretty much the same, saving our code there. I do like our earlier code because it's a little bit more clear about what's going on, right? So I think that is all for our problem here. Wow, the video has gone over 20 minutes due to long explanation and everything. So if you enjoy, I hope you learned something today. If you enjoyed the video, please like and subscribe. And if you have any questions, please comment below. And yeah, so if you want more material, check out the link in the description below. And have a good one. Yeah.